All right. So we're gonna start with chapter 12, which is kinetics. And as I mentioned yesterday, this first chapter does have a lot of sort of formulas and stuff, and I don't want to say it's extremely off topic of everything we're going to talk about for the rest of it or majority of it. It does relate a little bit to it, but again, we'll get into sort of this chapter first here with kinetics, and then we'll really get into the heart of the class in the next chapter and so on with equilibrium and stuff like that. So when we talk about kinetics, there's a couple of things that we're going to talk about, obviously, in this class. In this chapter, we're going to talk about kinetics, which is really how fast or slow a reaction sort of takes place. And we will also, in a later chapter, tie into something again that you sort of touched upon in Chem 50, which is enthalpy, which is sort of the first law of thermodynamics that has to do with energy. We'll talk about the other sort of thermodynamic sort of properties as well. But there is sort of a difference as we get to that chapter a little later on in the semester when we talk about thermodynamics. The one thing that a lot of times thermodynamics tries to sort of deal with is just the idea of whether or not a reaction will take place. And that's sort of the main sort of aspect of it. Under certain conditions, if you just kind of left the reaction alone, would you expect that reaction to actually take place and actually occur? Now, kinetics, on the other hand, as I mentioned, is really what we look at in how fast or slow a reaction may occur. How can we maybe affect how fast or slow a reaction occurs? How can we play with certain things to slow down a reaction if we need to slow it down? If we need to kind of speed it up, what we could do to kind of speed it up and stuff like that. So the focus of this chapter is kinetics. And when we talk about kinetics, oftentimes we talk about reaction rates or rates of reactions. And oftentimes, when we're talking about rates, we are talking about some unit of change over time. And most of the time, it is the change in the concentration over time. And it typically, usually, rates oftentimes will have units something like this, which is molarity per second. As we hopefully remember, molarity, right, is our moles per liter, right? And that is probably the most common unit of concentration that we see, especially with solutions. And that's oftentimes, if we're doing some type of kinetic study, like you'll do as well, we oftentimes will sort of follow how the concentration of something is changing over time, and that will give us our reaction rate. Now, if we had a simple reaction like A goes to B here, we could actually write what is sometimes referred to as sort of like a rate expression for this reaction. And the rate expression here, for example, is our reactants on this side, right, of the arrow. And on the right-hand side of the arrow, those are our products, right? So reactants, obviously, what we start with, products was making. So what happens in this case is when we look at our reactants here, and we want to write what is sometimes referred to as a rate expression, which is sort of what we see down here. The rate is equal to negative delta, the concentration of A over the change in time. So a couple symbols maybe you're familiar with. The delta symbol here does mean change usually. Also, when you see these sort of brackets, that usually means concentration. And for the most part, usually that is, again, molarity, which is the most common sort of unit of concentration. So here we're going to take the change in the concentration over the change in time. And it is going to be negative here for our reactants because as this reaction basically takes place, right, and this reaction happens as A goes to B, the concentration of A, should it be increasing with time or decreasing with time? What should happen to A? Should it go up or go down, this reaction? Should go down, right? Because in order to make products, you have to use up reactants, right? That's how you make products, right? We break all the bonds on the reactant side, they all reassemble, make new things on the product side. So in order to do that, we would expect the concentration, in this case of A, which is a reactant, should also be decreasing with time. Just like for B, we should actually expect the concentration of it to start to go up with time, right? Because as the A is being converted into B in this case, we will see an increase in the concentration of our products. So because this is a reactant, we do put this negative here in this expression. And we'll talk about why we do that in just a second, but that's typically what is done for reactants. So when you write a rate expression for anything with reactants, which should be decreasing with time, you will have that kind of negative in the front there of that sort of rate expression. On the B side here, or the product side, we are gaining products with time. So we do have the change in the concentration of our products over the change in time. Here, though, there is no negative included. Now, the reason why, for example, we include the negative on one, but not on the other, is because one thing that you should remember as you sort of go through and write sort of rates and stuff like that, or calculate rates, is rates are typically should be positive numbers. So when you calculate a rate, it should typically be a actual positive sort of number. And if we think about what's happening here in terms of just this reaction, if we sort of just made up some numbers here, over here. So obviously here, let's just say initially, if we had our A and our B, and initially we had like 4 molar of this guy, initially maybe we had nothing of this guy here to start with. And when this reaction is done, at the end of it, we would expect maybe we had like 2 molar of this, and maybe we made like 3 molar of this, right? So when we calculate, for example, something like the change in the concentration of A, that basically is the concentration of A final minus the concentration of A initial. So when I do that for A, what I end up with is, in my made up example here, basically 2 molar minus 4 molar, which will give us negative 2 molar. So we're going to get a negative number when we do that top part there. And that negative, along with this negative here, will turn our rate into a positive number. So that is why we have sort of the negative on that expression, because the reaction should always be decreasing with time, which means every time you calculate the change in its concentration, you should end up with a negative number. And again, those two negatives will then become a positive rate, which is what we want at the end. We don't need that for B, for example. If we take a look at B, the final was 3 molar minus 0 molar, which is our initial. We actually end up with a positive change in the concentration. And that is why we don't have the negative here. Again, that's going to allow us just to get a positive value for rate. So only for reactants, we sort of include that negative, and really is sort of to, because they're always going to give you sort of a negative change in concentration, that's going to again turn that rate into a positive number. Question. Now, again, a lot of times in kinetics, and you'll see this as we go through this chapter and some of the experiments that we do, a lot of times there's a lot of graphs that we see in kinetics, and like things would like to be sort of graphed as you go through it. But again, over a period of time, we could see here, we would expect, at kind of time zero, if you will, we pretty much have all of reactants present. So you can see here, these are the black circles, and that represents A in this reaction. And pretty much it's all reactants at the beginning of this reaction. As we start converting some of those reactants into products, we start to see some of those red guys coming in there, and we start to produce some red products. And if we look at it graph-wise, we do see, as we were just talking about, basically we're going to see our reactants start to decrease, and here's our products is starting to increase with time. And that is especially what we expect. At some point, we'll kind of run out almost of products, reactants, and we can't make any more products at that point. So you can see at sort of the end of the reaction, mainly products present. We still have a little bit of reactants, but almost all the way there. Now, one of the most common ways that we can sort of follow the change in concentration, say in an experiment or something like that, is especially if we have a reaction where there's some type of color present, we can actually follow the change in the color of the reaction, and that will also help us figure out how the concentration of everybody is changing. So when we look at this reaction here, which is some bromine plus some formic acid, this Br2 is actually this color here. So we could see at the very beginning of the reaction, we have mainly reactants present, because pretty much everything on this side is colorless. Yeah. So like everything on the product side there is colorless in this particular reaction. So obviously, I can see as time goes on, as we start converting more reactants into products, we start to see actually the color start to change. It goes from a kind of reddish orange to a lighter orange to a lighter orange, getting towards that yellow side, and then eventually to sort of colorless at the end, which would imply that we probably have now converted mostly things into products. We don't have a lot of reactants present. Now, one of the things that we could do in this, and you also do in a kinetics experiment coming up, is we can follow the absorbance of these solutions because there is a color involved. And we could use something like a spectrometer, like a spec 20 or something like that, where basically, as you can see here, you shoot a wavelength, you shoot light of a specific wavelength through your sample, and it goes to a detector. And usually when we do these type of experiments, we do want to set our wavelength to a specific wavelength. And that's really what this graph is. And you will actually do this when you do your experiments as well, is you typically will take probably your darkest solution, usually a lot of times, or a solution that's probably the darkest in color. And you will basically test the absorbance at different wavelengths. And what you will typically see is you will typically see kind of like a peak, and that's the wavelength, which is lambda, maximum absorbance. And that's usually where you want to kind of set your spectrometer to. And that's because, for example, if I was doing this experiment here and I set my wavelength way over here, that's about as much absorbance as I'm going to get out of that, which means probably most of my samples are just going to be off the scale, right? Because pop back, I think. It's going to be off the scale there because that's as much absorbance as we get. Now, if I set my wavelength way over here, I have all this that I can basically take measurements in terms of absorbance, all that absorbance values, and that's going to allow pretty much all my samples to be able to be read by the machine. So one of the things you do, the old way of doing that is you physically have to kind of move the thing, everything to different wavelengths, take absorbance values. Nice fancy equipment we have nowadays will just do it on a bunch of wavelengths all at once for you really quick and give you the graph. And what you do typically is kind of move your thing around and go, okay, this looks like the good wavelength to kind of lock in. And that's what you'll use. One of the other things that maybe you're familiar with as well, the color that we see in the solution, for example, is not the color that we would set the wavelength to, because the color that we see is actually the complementary color to what is being absorbed. So if you have kind of like a red solution, you would not set your wavelength in the red part of the visible part of the spectrum. But remembers the visible part of the spectrum, right? Red, orange, yellow, green, blue, indigo, violet. Yeah, so wavelengths like 700 nanometers, 400 nanometers in that range. So we would set our wavelength to, something maybe in the greenish blue sort of area, which is sort of the complementary color to red. Now, why does this work? Because the way this sort of process works is we typically measure one of two things. We measure absorbance, which is basically how much light is being absorbed by the solution versus what reaches the detector. Or sometimes, not too much these days, people sometimes can record percent transmittance, which is basically the ratio of the light that goes into how much reaches the detector. But most of the time, we record these sort of absorbance values. So if I had a really dark colored solution like I do here at the very beginning, would I expect my absorbance value to be high or low? Thank you very much. Is a 50-50 shot there. You can only be wrong once unless you guess twice and not the right answer twice. What do you think? So if absorbance is how much light gets absorbed by the solution, right? The darker the solution is, the higher the absorbance you have, right? So like this, right? So if it's going through this, all the light's going to get caught there by the dark color, right? If there's like this with nothing there in terms of color, just going to go right through, right? So it's not going to be absorbed at all. So the darker the solution is related to the absorbance value that you see. So the darker the solution, you would have a much higher absorbance on this end than over here, where you probably have no absorbance. You have a much lower absorbance value on this end of the spectrum. So what that allows us to do, for example, is we very much can just follow an experiment. This is actually what you'll do. You could follow the change in the absorbance values over time. And if you have a lot of high absorbance values to begin with, that means you have a lot of concentration of whatever is the colored solution. If you have low absorbance values that go to high, then you're making something that obviously has a lot of color at the end of it. In this experiment here, we would probably have very high absorbance values to begin with. And at the end here, we would have very, very low absorbance values. So our like graph would look very high to begin with, and then it would probably level off in terms of its absorbance values as we get to the end, because again, we're coming to something that is a lot less color. So in this particular case, because the BR2 has the color, we could relate the concentration change of the BR2, which is that color, is proportional, and that's what that little symbol means. That's the proportional symbol to the change in the absorbance value. So this is a very common kinetics technique that we use. And again, we'll use it to some extent in part two of the experiment we're starting today, but we'll really use it when we get into kinetics experiments. And this is a very, very good way to do this. Would this be a really good way if there was a reaction where there was no color ever? This would be a really terrible technique to try to use if you had no color anywhere, because you're basically just going to have your patient died, basically flat line, right? You're going to have no absorbance. It's just going to be zero all the way through the experiment and stuff like that. So this is a really good technique. Obviously, like I said, if you have something, and it could actually be on either side of the arrow, you could have something where, you know, you got some color on the reactant side and maybe it's colorless on the product, like in this reaction. Or and you'll do an experiment like that where you kind of start with it, a lot of color, and then it kind of decreases over time. Or there's experiments where you start with something that has no color, and then all of a sudden, sort of the color appears and stuff like that. And so this is a good sort of technique to do that. As I mentioned before, there's a lot of graphs sort of in kinetics, and this, for example, is a graph of some experimental data that would be done in this sort of experiment. And you can see on the y-axis here, we're plotting the concentration of BR2. On the x there, we are looking at it over a period of time. And as you can see, we do see that the concentration of BR2 starts up high and it is obviously decreasing with time, which is what we would expect here since BR2 is a reactant. So it should be getting used up over time to make our products. Now, when we talk about rates, sometimes we talk about rates, a couple different types of rates. A lot of times we focus in on sort of the average rate, which is kind of like the difference in the concentration from the final to basically the end of the reaction, basically. So from final to the initial, difference between final to the initial of the reaction over the whole period of time. But sometimes we're maybe interested in, you know, what will the rate be at this particular point in time? And that is sometimes was referred to as like an instantaneous rate, like this particular point in time. The way I think about it is this. You could think about it like if you were driving from, say, here to Arizona, right? Along your trip there, maybe you average 75 miles per hour as you're driving there. But along the way, at different periods of time, maybe you're doing 55, 65, 75, 85, 95. Just where you cross over that border and go, wow, cool. It's like 75 miles an hour here. That seems like 105 seems reasonable at this point. Maybe I'll just go that far, right? Hopefully the cop's not behind you when you're instantaneously doing 105, right? Which I would not recommend for anybody listening. Don't do that. Safety warning. But you know, your instantaneous rate along the way may vary, right? So you're not going to always be driving at the same rate all the way through when you're on the freeway or just driving in general. So if you average out your whole trip, maybe you did drive only 75 miles an hour, you know, for the whole trip, but there were points that maybe you were moving faster. There were points maybe you were moving slower. And those are sort of like those instantaneous moments along the way that you may actually have a different rate for that particular point in time than you when you compare it to kind of your whole trip. And that's what we see here. And one of the ways that you can sort of calculate sort of that type of like, I want to know what the rate is in this situation is you could take the slope of the tangent of these lines. And if you're not familiar with that, basically you could see that at 100 seconds, that's our rate. At 200 seconds, slightly different rate. 300 seconds, we really drop down a lot right at the end here as we're nearing the end of it. So at those particular kind of points in time, we do have sort of different rates. The way that you could calculate this graph is not technically a linear graph, which a lot of times in kinetics we like nice linear lines and stuff like that. But you can take the slope of the tangent, which means basically if you were looking, for example, at this point in time where they have it here, what you essentially want to do is draw a best fit line that basically touches that point. So that's really this part of the line here. You want to do a straight line that basically kind of comes across there and just touches, as bad as my drawn straight line there is, just sort of touches that point. And then basically what you want to do is basically what we see down here, you basically want to take the slope of that line. Yeah. So you're going to take the rise over the run, basically. So you're going to find 2 points on that line that you did, and you're basically going to calculate the slope of it, which is rise over run, which in this case is the change in the concentration of BR2 over the change in time. And that's what we have here. And so sometimes if you're looking for just what the rate is at a specific moment in time, it does require you to grab a ruler, do a straight line, and again, on that straight line that touches the point that you're looking for, that's basically how you figure out the slope of the tangent. You basically just take the slope of that kind of straight line that you drew. To help you out, sometimes if you're doing it, you maybe want to extend your line kind of far on each end if you're going to draw kind of a straight line, because that way you can kind of find a nice easy point or two there that you could kind of use. Like usually when you calculate the slope, you may not want to always use the end of the line, but somewhere on the line or near it is usually pretty good. And that's what they did there. And that's what basically this is. They're just kind of showing you that you're going to take basically the slope of each of those lines. So also here they kind of drew a line, and here they kind of drew a line, and they basically take the slope of each of those lines. And again, that's how they come up with those sort of instantaneous rates at that particular point in time. Any questions out there? And again, you can see here as you look at this, it does make sense. The rate is a lot higher at the first point where they took it and much lower at the bottom, right? Because at the bottom, we have now used up a good amount of our reactants. So we don't have as many reactants, right, floating around. And that's going to take longer for reaction to occur. There are certain factors, right, that affect how fast the reaction takes place. One of the main things is like the presence of things, right? So if you have a really high concentration to begin with of reactant molecules, they don't have to go find people, right? They're just going to run into everybody really quickly. But as that concentration of reactant molecule starts to decrease, it's going to take longer for everybody to go find each other to start reacting and making products. So that's why we do see typically as the reaction progresses, the concentration of our reaction starts to decrease, and we do start to see a decrease in the rate as we get to the end, because there's just not as many reactant molecules as we had at the very beginning of the reaction, where basically just turn around, they're going to find somebody to react with really quickly. Any questions on that? Now, when we look at some more data for this sort of experiment here, and we look at this graph, there's a couple of things that we actually do see, and it's a very common thing that we do here in kinetics, which is a lot of times we do like this sort of linear relationship that we can get. And as we saw here, if you look at just the instantaneous rate there at a specific period of time, what you will see is obviously you get some different values all the way through. Now, if we wrote sort of this thing right here, which is sometimes referred to as like a rate law, we solve for this little k here. And in this case, as you can see, k would equal our rate divided by BR2 concentration. What we end up seeing is in this column, we pretty much see a constant value for that little k. And that little k, and I write little k because as we will talk about in the next chapters, and pretty much what this class is brought to you by is the letter k. We will talk about capital K, which is the equilibrium constant. So capital K is actually different than little k, which is the rate constant in this case. And this is the rate constant And it is actually, much like the name implies, it is a constant sort of value for a particular reaction under a set of conditions. So if you did this experiment here and you want to calculate the rate constant, you would get this sort of constant value for it. In this particular example here, you can see it is 3.5 times 10 to the minus 3 reciprocal seconds. Number not important at all really for us or anything like that. But uh, the units, as we will talk about, and one of the things that the rate constant is useful in understanding is when you see certain units associated with the rate constant, it often will tell you what type of reaction you're dealing with. And we'll talk about different types of reactions in this chapter, things like first order reactions, zero order reactions, second order reactions. So actually, when you take a look at the units, it actually will give you that information of, oh, we're dealing with like a first order reaction, second order, or zero order. By the way, reciprocal seconds is typical of a first order type reaction, as we will see a little bit later on in this chapter. So the other thing you think of in terms of the rate constant is essentially is tells you how fast or slow a reaction will take place. So if you have a really high value for a rate constant, you probably will have a pretty fast reaction. And if you have more of a lower value for it, it may not be as fast. You can just think about it mathematically here. Obviously, if the rate of the reaction is equal to K times the concentration, if this number gets larger, the K value gets larger, then your rate's going to get larger, right? And if the K value is smaller, you're going to end up with a smaller number and your rate will kind of slow down. So you kind of think of the rate constant as sort of how fast or slow a reaction is taking place. Now, what happens if we actually do an experiment, for example, where we really don't have color? Now, I know there's color in this, but I believe they just put it in there so you can actually see there was something in the flask, but there's really not color. So pretty much all this is colorless. And in this particular case, as we talked about earlier, this would not be perhaps a good idea to try to do any type of absorbance type of experiment. Again, you're not going to get very much happening in that situation. But one of the things that we do see in this particular reaction that can help us is we are actually forming a gas. Yeah? And when we're forming a gas in this particular case, one of the things that we could actually kind of use to our advantage is our friend PV equals nRT. That is, hopefully you remember the ideal gas law, right? And pressure here needs to be in atmospheres, right? Volume needs to be in liters. N should be moles. R is the gas constant, 0.08206 liters atmosphere Kelvin mole. And temperature is in Kelvin, right? Could also use 0.0821 if you remember that number as well. So how can this help us? Well, if there's really no color, but there is definitely a gas being formed, we could look for the presence of pressure to basically occur. And if I take the ideal gas law here and I actually solve for N over V, that will equal P over RT. Now, if I rearrange that again and solve that to rearrange that, I can divide that to this side and divide that to that side, right? It's basically how I get there. And that's important because, again, N here is moles, and V in this case is liters, and moles per liter is the molarity, right? So here we can actually figure out the molarity of the gas or how it's changing by actually just following the pressure. Because if you did this experiment, R is a constant. You probably will do this experiment at the same temperature in the same room. You're not going to probably change the temperature, which means really the only thing you would have to sort of follow in this type of reaction is you just need to follow the change in pressure. And the change in pressure will then can be related to how the concentration of, in this particular case, O2 is changing. We could do this because, again, O2 in this example is the only gas that we have present. So we will not have pressure until we make O2, right? So until we start producing some O2, we will not have any pressure. And as we start producing a lot of O2, we will start to see the pressure increase. And that would mean we have a lot more O2 present and a higher concentration. So this is a way, again, that you could do sort of a kinetic study and figure out the rate of what's going on here with our product in this case, because it is a gas, and we can basically just keep following the change in pressure over time, which we again can relate to the change in the concentration. Again, because our temperature is not going to change, our R is going to be the same. So just by simply following that over the change in time will allow you to do sort of a kinetic study. So there are other ways, obviously, instead of just absorbance, when you have colors, that you can do these type of studies as well. Any questions on that there? Yeah. The the rate constant is a little K, yeah. T are we talking about on this slide? The ideal gas law, say it one more time.
Where you wrote on the side PV and RT,
Uh-huh.
T equals K. Is that
I'm sorry, that's Kelvin. I'm sorry, that's just Kelvin. Yeah, that's I'm like, where's the K we're talking about here? I'm like, yeah, yeah. So no, temperature, like most things in chemistry, right? Temperature, pretty much a no-brainer on that. On most things in chemistry, it's got to be like Kelvin. Only time probably you ever left it in Celsius is when you did like specific heat. A lot of times, but most of the time it's like automatic, like should convert to Kelvin. So yeah. Other questions? All right. So here is actually a graph of that, and we see the graph actually looks a little bit different, that it goes higher with time. And that's because, again, here we are following the pressure. And remember that we're only going to start to get pressure when we start to make products. So at the beginning of this reaction, we pretty much have no products being made. So as we start to make products, we start to see our graph increase with time in this case. And that's, again, because we're following O2 and we're making some products over time. Just like we talked about before, you can see it again on here. If we wanted to know at this particular point here, sort of that instantaneous rate, we would draw our kind of best fit line again that kind of goes through it, and then take the slope of that line. And in this case, we do get something like 0.12 millimeters of mercury per minute. Millimeters of mercury obviously is a unit of pressure, right? So a reminder, 1 atmosphere, right, equals 760 torr and 760 millimeters of mercury, right? So basically, if you just kind of take a quick shot of it of our rise over run and our slope, you would take maybe like that way, and maybe you're like 90-ish, right? And down here, wherever it was, maybe you're like 40-ish. So you take that difference, ballpark of 50. And then you do the same thing coming down this way, maybe you're like 200. And on this side, I don't know, maybe like 620, maybe. And maybe that's like a 420, maybe. And so basically you take 50 divided by 420, you're probably in the ballpark there at 0.12. And again, that's how you would sort of figure out the slope of the tangent of that kind of straight line. You just want to take obviously 2 points, right? Difference in the rise over the difference in the run, difference in y over difference in x. And what you get there will give you, again, that sort of instantaneous rate for this particular case. And it is in basically pressure versus time. And again, that is also a rate as well. Any questions on that there? Let's see how bad I did. I think 50 divided by 420. 0.119, pretty close. Rough estimates like that. All right. So let's talk about reaction rates and rate expressions and everybody's other favorite thing, which is stoichiometry, right? So always when we have a chemical reaction, things do not react always in like a one-to-one sort of relationship, right? And that's the idea of stoichiometry, where you can use the coefficients in the balanced equation as the moles of each of those things, right? So we were looking at this equation here. We could say basically for every 2 moles of A, it reacts, or it forms 1 mole of B. And again, those are just the coefficients from the balanced equation. So we could actually write a rate expression for each of those things in this reaction. And again, we're going to take the rate is equal to, for our A, it is a reactant, so we will have a negative. And now to take into account the stoichiometry of the equation and sort of the kinetics all together in one move, what you could do is basically take 1 over the coefficient. So that is how we get this aff here. It is 1 over our coefficients is basically how we get there. Again, the change in the concentration of A over the change in time. Now on this side here, their coefficient is 1. Once again, as we talked about with our products, it's increasing with time, so we do not need the negative in our rate expression. And this is basically, although we would never probably write it, it's basically 1 over 1 in this case, right? So 1 over the coefficient obviously would just get you 1. Change in concentration of B over the change in time in this case. So in general, you can, if you have an equation, write a rate expression for anybody in the equation by taking basically 1 over the coefficient, the change in the concentration of the reactant over the change of time, or change in concentration of product over the change of time. So here, because A is a reactant, we have our negative. Because B is a reactant, we do have our negative. And once we get over to C and D, they are our products, so no negatives involved there, as that should give you a positive sort of change that's going to occur. Now, why is this helpful? This is helpful because, frankly, if you know basically just like one piece of information about the reaction, you basically can figure out how everybody else is changing with time. So, for example, if you knew the rate of the reaction, you could figure out how A is changing with time, B is changing with time, C is changing with time, or D is changing with time. Or if you knew how just C is changing with time, you could figure out basically how everybody else is changing and the average rate. You could obviously, as you can see here, they are all equal to each other. You could do it like that. You could do it very much like what we see up on top. You could just pull out. So let's say you were just interested in A and D in this reaction. You could just write 2 separate rate expressions. The rate for A would be minus 1 over A, the change in the concentration of A over the change in time. You could also write the same sort of one for D, which once again would be positive because it's a product. So 1 over the coefficient, change in concentration of D over the change in time. And let's just say you knew how A was changing. So let's just say you knew this information right here. You would be able to plug it in and actually get a value for the rate. The nice thing about that is that rate is the same average rate for this guy. So you would then know the rate of the one on the bottom, which would then allow you to solve for something like how D is changing with time. So by just knowing one piece of information, you basically could figure out how everybody is changing with time with that one piece of information. A couple of things here. When you calculate typically the average rate or the rate of the reaction here, as I mentioned earlier, should be a positive number. Yeah, so you should end up with a positive number. Now, if you are asked a question how a specific reactant is changing with time, the rate that you get will probably end up being a negative number. Again, it should be decreasing with time. So if you are solving for just this guy right here, that probably is going to end up being a negative number. If you were just solving for this guy, that would end up being a negative number. If you did this guy, that would end up being a positive number. And if you did how D was changing with time, it would also end up being a positive number. So if you were asked a question where you're asked, how is A changing with time, it is possible that your final answer will be negative because that would imply that A is decreasing with time and you should end up with a negative rate. But if you're solving for something how D is changing with time, that will end up being more of a positive number. But definitely the average rate of the overall reaction should usually be a positive number when it's all said and done. Any questions on that? Yeah.
Now a reactor has
It's negative because the overall idea here is our reactants, right? When we start with, they has to be used up to make products, right? So as they get used up, the concentration of your reactants is going to start to decrease with time, which means when you calculate something, say like for A, the change in the concentration of A, if you are following A's concentration over time, at time 0, maybe like I said earlier, you had maybe like 4 molar to start with. But as this reaction continues, the concentration of A is going to start to go down. So let's just say the end of the reaction was like 30 seconds later. and maybe you're left with just like 1 molar of A sort of left there. When you go to calculate this, which is basically the concentration of A final minus concentration of A initial, when you do that, that will basically be 1 molar minus 3 molar, 4 molar, which will give us -3 molar, which is how this guy is changing with that period of time. Basically, it's changing by 3 molar for every 30 seconds, right? And that negative that you would get when you would calculate that part here needs to be sort of counteracted with this negative, because then that will turn your rate into a positive number. Otherwise, you'll end up with a negative rate for the overall reaction. But as I was mentioning a second ago, if you were asked, how A is changing in this 30 seconds, you would, kind of put the 30 seconds, and now you would end up with a negative number in terms of just A by itself, because A is decreasing with time. So you will end up with a negative rate for A by itself. But that's why for reactants, because all reactants should be decreasing with time, every time you do kind of final minus initial, that should yield you a negative number, which then needs to be sort of counteracted with that negatives in front. Other questions? Yeah. How about we do a problem? That sound good? Yeah. So it's coming up. We're gonna actually do some with some numbers here and see how we kind of relate that. But just to quickly answer your question, in that example, we basically knew how A was changing. So basically, if you just think about mathematically, what we would have when we look at the rate is equal to -1/A, the change in concentration of A over the change in time. We basically have all these numbers on this side, which would allow us to get this number. And because, as you can see here, everybody's equal to each other, the rate for A, average rate for A is the average rate for B, is the average rate for C, is the average rate for D. So once you would know this rate, it is going to be the exact same number for our products, because that's the average rate of the overall reaction, and it applies basically to everybody there. Yeah. So that's how they kind of relate to each other. All right. Why don't we first, before we get to one with some numbers, why don't you write the rate expression for each of these guys here in this reaction? Okay, so let's take a look. So again, here, if we're just going to write the rate expression, we can start with the rate is equal to, we can start with our first reactant. Again, because it's a reactant, we know we do need the negative here because it's decreasing with time. It's going to be 1 over the coefficient. So obviously the coefficient here is 1. So we really don't need to write 1 over 1 or anything like that. We're going to do our change in the concentration of CH4 over the change in time. We could then say that's equal to our next reactant, which will again need a negative because it's decreasing with time. Here we do have a coefficient of 2, and we could take 1 over 2. And again, taking the 1 over 2 basically takes care of the mole-to-mole relationship to stoichiometry. As we'll see in an example coming up, you could just do a stoichiometry problem first with like a regular kind of stoichiometry sort of move, and then kind of tie all the kinetics aspect into it and at the end. Or you could do 1 over the coefficient. It kind of just does it all together, and you don't have to kind of maybe do separate sort of calculations. But you can, as we'll see in an example coming up, kind of do just stoichiometry by itself and then the kinetics part of it. This would be the change in the concentration of O2 over the change in time. We're now going to our product side, which again should be increasing with time, so we don't need any negatives here. Once again, the coefficient here is 1, so we would not go 1 over 1, but essentially what's going on there. And that would be the change in concentration of CO2 over the change in time. And lastly here, H2O being a product as well, going to go 1 over the coefficient, change in the concentration of H2O over the change in time. Now, again, once again, you could write it all like this. You could individually just write it for each thing. And the thing that sort of ties everybody together is that rate, and it's the average rate for the overall reaction. So whatever this guy is basically equal to this, and then that rate is equal to this guy, and that rate is equal to this guy, and so forth all the way across there. So that's sort of what ties them together, is what they're all related to each other. Any questions on that there? So why don't we try one here with some numbers and do some calculations here. So for the reaction below, if the concentration of I minus changes from 1 molar to 0.868 molar in the first 10 seconds, calculate the average rate for the first 10 seconds. and what is the change in the concentration of H plus over the change in time. So that is sort of what we're. Okay, let's take a look, see how you're doing. So a couple things are given to us in this sort of problem. Obviously, we have our initial concentration of I minus, which is 1 molar. We have our final concentration here of I minus, which is 0.868 in the first 10 seconds. So for our time, if you want final, 10 seconds, and maybe our initial here would be 0 seconds, probably safe to assume. So we obviously have information about I minus here, and we are looking for the average rate and how H plus is changing with time. So we're definitely interested in those two things in that equation. Honestly, we can pretty much ignore everybody else in the equation. We're just interested really in those two things. So the thing that you could do is obviously, as we've talked about, you can write a rate expression for each of those. So if we were doing it for the I minus, we would do it just like we talked about in the last one as well. The rate here, since I minus is a reactant, it would be negative 1 over the coefficient, which is 3 in this case, again, to take into account the sort of stoichiometry change in the concentration of I minus over the change in time. Since we're also interested in H plus, we could write a sort of equivalent rate expression for that, which would be the rate is equal to H plus here is also still a reactant. So this is going to be negative 1 over our coefficient, which is 2. So 1 over 2. Again, that's going to take the stoichiometry into account. Change in concentration of H plus over the change in time. Do you have any questions on that so far? At this point, the only piece of information we really have is about I minus. So this is the rate expression that we want to start with because that's the information we have. So here we would go, the rate is equal to minus 1 over 3. Now remember, we do want to do final minus initial here. So our final is 0.868 minus 1 molar. And we could also do final, which is 10 minus 0 seconds, right? The reason I want to do final minus initial is what type of number do I get on top there? Negative, right? So again here, if you did just the difference, you will end up with a negative overall rate, which we don't want, right? So we want to make sure we do the final minus initial here. So that is going to get us, again, that negative number. That's important for why we put the negative here to make sure that we do end up with a positive value for our rate. Any questions on that there? So let's pop the numbers in and see what we get here. 0.868 minus 1 divided by 10, and don't forget divided by 3. And again, that gets you negative 0.0044, and then you still have the negative in front, which turns it into a positive rate, which is what we're looking for, of 0.0044. By the way, the units here are molarity per seconds, right? Because nothing cancels out, and you should have some units associated with that. Now, that is our average rate for this reaction. So again, if you want to relate to what we were talking about earlier, that is the average rate you were driving from here to Arizona, right? Like 75 miles an hour. This reaction overall is moving at this rate when you take everybody sort of into account. The average rate at the end here for the overall reaction should be positive. Yeah. Now, when we look at the other part of the question, which is we're not interested maybe in the overall sort of average rate of the entire thing, but we're interested in how, in this case, a specific reactant is changing with time, which is the H plus. That is what we're going to try to solve for now. Because this rate that we just calculated is the average rate, this number is the exact same number that we would have for our H plus now. So now we have our H plus sort of average rate, and we can solve for this basically. So if we take that rate expression we had for our other reactant, and we take the average rate that we just solved for, that means that this whole thing here is equal to 0.0044 molar seconds, right? Now, again, I do want to solve for this, right? So that is what I'm looking for in this case. So how do I solve for that? What do I need to do? I need to take the 2 and multiply it to the other side, but not just the 2. What else is there? The negative, right? So we got to take that to the other side. So we're going to multiply the -2 to the other side. Uh, and if you do that, that will give you how H plus is changing with time. And if we do that, we're going to basically take the -2 to both sides and do that. It's going to give us 0.0088 molar seconds, and that's going to be negative, right? And this is okay that we get a negative for this one because, again, this is a reactant, and we're looking how the reactant is changing with time, and it is changing negatively. It's decreasing with time, so we would expect for the reactant here to be a negative value. First up, any questions on that there? Yeah. So by doing the 1 over the coefficient, like I said before, it kind of just wraps the stoichiometry, the mole-mole relationship into the calculation, and that's essentially what we're doing. The rate at which H plus is changing with time, is it changing faster or slower than the average rate? It is about twice as fast, right? And it has a coefficient of 2, right? So again, that stoichiometry, that mole to mole relationship affects it, right? So you got twice as much sort of reacting as sort of the overall sort of rate of the reaction as well. And again, taking into account with everybody else in that reaction, everybody's on an average reacting at 0.0044 molar seconds, molarity per second. So again, if you're not sure what that actually means, it means that the concentration H plus is decreasing by 0.0088 molar every second. Yeah. So you're losing that much concentration every second of this reaction. Yeah. Um, yeah. So for example, you could be asked something like that if for example, if your question is you know, how much the concentration would change over like 60 seconds or something. It's in this case that's essentially what you do. You times that by 60, for example, and that'll give you at tests for 60 seconds. You would expect it to probably change this much in terms of its concentration. So that is potentially something that could be asked. Yeah. Other questions? All right. Let's try another one here. If we have 2.4 times 10 to the 2 grams of NOBR, the molar mass of NOBR is 109.91 grams per mole. It decomposes in a 2 times 10 to the 2 milliliter flask in 5 minutes. What is the average rate of BR2 that's being made there in molarity per second? So give it a go, see what you come up with. All right, let's take a look and see on this one. So again, we're given some information about the decomposition of NOBR. So clearly we got some interest in this. And we're looking for BR2, so we got some interest in this. So once again, we could kind of just write our rate expressions for those two and see where we're got. So again, for our reactant, our rate here would equal -1 over the coefficient, change in the concentration of NOBR over the change in time. For our product there, the rate is equal to coefficient is 1, so 1 over 1, change in the concentration of BR2 over the change in time. In this particular case, we're not really given the molarity or anything like that. We're just kind of given the grams of what decompose and the volume. And from the grams and the volume and the molar mass, we can get molarity, right, which is our moles per liter. So I'm going to get my molarity here of NOBR, which is pretty much the only information that's sort of given to me. So we're going to do a little 2.4 times 10 to the minus or 10 to the 2 grams of NOBR. We're going to divide it by the molar mass, which they nicely gave you. Obviously, if they did not give it to you, you would have to go find your periodic table, right? And all that good stuff. And 2.4 to the 2 divided by 109.91. And going to get us, we'll call it 2.1836 moles. I do have the volume here, which is 2 times 10 to the 2 milliliters, or that is 200 milliliters. Or if I divide it by 1,000, that is 0.2 liters, right? So now I have moles of my NOBR, and I really have my volume. So that will allow me to get to the molarity here. So the molarity here of the NOBR, which is going to be decomposed, is going to be our 2.1836 moles divided by our zero point 0.2 liters. And using the whole number there, I go 10.918 molar in this case. Yeah. Questions on that there? By the way, that equals in my formula over here the change in the concentration of NOBR. Now, in terms of time, we do have time that's in 5 minutes. I'm going to convert my time into seconds because ultimately my answer's got to get to seconds anyway, so might as well convert it to seconds here. So, a minute, I think, is 60 seconds, they say, is 300 seconds. Yeah. And by the way, that would essentially be the bottom part here. So I got my molarity and I got my time. I now have really everything in the right units, if you will, to figure out the average rate of the reaction. Any question on that so far? Okay. So let's actually do that then. We can now plug into here. The rate is equal to minus 1 over 2. My change in the concentration is going to be negative 10.918 molar divided by 300 seconds. Why did I make it negative? Yeah, because it is a reactant. So although they didn't explicitly tell you that here, the way that we would get that number right, we would take final minus initial. And since it's a reactant and decreasing with time, it should probably be a negative number, right? When you get in there. That way, that negative there, right? And that negative there is going to turn our rate again into a positive. Just like, although we didn't really calculate it this way, how we probably would have got the final temperature or the temperatures, not temperature, the time change there would be final minus initial, final minus obviously being 300 seconds minus 0, which would be our initial seconds.
They don't specify how much of the reactant is.
Yeah, and that's the other assumption here. We're kind of assuming in this case the whole thing is going to get used up in this particular. Otherwise, you wouldn't really know. So ideally, the assumption for this is that pretty much all that's just going to get used up basically. Yeah. Other questions? Now they told you like, hey, you use in that time you used up only like say 50% of it or something, then you could adjust it. But obviously they would have to give you that information. Otherwise, it's probably safe to assume. Other questions? All right, so yeah, we should probably punch that through a calculator, huh? That would be good. Let's take that divided by 300. So 10.918 divided by 300, also get divided by 2, which is 1 over 2, is going to get me I'll use the number there. Come here, 300. Gets me a 0.018 here. I'd go with that, I think. Looks like everybody's 2 sig figs. We'll go with that. And this would be molarity per second. This again would be our average rate for this reaction. Now, again, we did get a positive number, which is what we're looking for. We now can relate it to our BR2 over the change in time. And what we see is the rate is equal to the change in the concentration of BR2 over the change in time. And since the rate equals 0.018, that would be our answer in this case. Yeah, so it is the same. So in this particular case, the production of BR2 is basically rolling the same as the average rate in this reaction is being made at the same rate. There's up any questions on that there? Now, as I mentioned before, obviously by taking 1 over the coefficient here, We are just kind of tying the kind of stoichiometry together with the kinetics part of it. As I also mentioned before, if you wanted to take just a more kind of like stoichiometry approach first and then kind of tie all the kinetics aspect to it, you could do that. So, for example, if we were going to do that, we would kind of start the same way. We'd figure out our moles of our NOBR, and you could take your moles of your NOBR and just like a normal sort of stoichiometry move, you could just do the mole to mole relationship from the equation, which is obviously 2 moles of NOBR gives you 1 mole of Br2. And if you do that there, you will end up with 2.1836 divided by 2. You end up with like a 1.0918 moles of Br2. Now you could kind of just put in all the kinetics aspect of it. You could turn that into molarity by dividing it by zero point 0.2 liters to get the molarity of the Br2. So if you divide that by 0.2, you'll get 5.459 molar seconds here. And not seconds because we haven't done the time part. That's just the molarity. The molarity of it. And now you can tie that into your kinetics equation here. This guy, we now have our 5.459 molar divided by our 300 seconds and divide that by 300 seconds. And you end up with your kind of same 0.018 molar seconds. So you could kind of do like a stoichiometry and then kind of do all the kinetics part of it at that point, and you get the same answer. Or you could just kind of tie it all together in one calculation. So you can do it either way, whichever way you kind of prefer. But sometimes the 1 over coefficient is a good way to do it because, kind of just keeps everything together and the kinetics part of it and the stoichiometry part of it. Any questions? So let's talk a little bit here to finish up on for today, some factors that affect the rates of reactions. The nature of things that are reacting can have an effect on how fast or slow a reaction takes place. Small molecules do tend to react faster than larger ones. Gases react faster than liquids and liquids faster than solids. Gases have a lot of energy, right? So, and they're moving around constantly, so can't come in contact, right? Remember that for a reaction to take place, you basically need 2 things that sort of happen. You need something to collide in the right spot, and it does have to have the right amount of energy to allow everybody to start breaking bonds and making bonds. Certain types of chemicals react faster than others. We've done some of those single replacement reactions where activity series. Some metals are more reactive than others. Ions as well are found in solutions and they're floating around. So they're actually just good to go at that point, right? They just need to run into somebody if they want to react. They don't have to like break bonds or anything like that. Temperature is a really big factor in terms of how fast or slow a reaction will take place because there is this minimum amount of energy that's needed for actual products to be made. The higher the temperature you do, or the more you increase the temperature, typically you usually will increase the rate of the reaction just because when you increase temperature, you're adding a lot more energy into the fold and things will have a lot more energy. If you light a fire underneath somebody, it said they move faster, right? And they have a lot more energy, right? So that's the same idea here as you increase the temperature, you have a greater number of reactant molecules that have enough energy basically to get to the other side and make products, basically. The opposite is true. If you lower the temperature, like for all your stuff on ice, you're basically taking out a lot of energy from that reaction and everybody's going to kind of slow down. So it's going to take longer for things to kind of come in contact with each other. It's going to, when they do come in contact with each other, they may actually not possess enough energy to get to the other side when they do collide and stuff like that. General rule of thumb, as you can see there, if you increase the temperature about 10 degrees Celsius, for a lot of reactions, that's enough to like double how fast it will kind of happen or the rate of reaction. We will see the Arrhenius equation later on in this chapter, which basically deals with the temperature relationship to the rate of the reaction and how fast or slow it sort of takes place. Catalysts are another things that can affect the rate of the reaction. If you're not sure what a catalyst is, it is definitely not a reactant. It's not a product. and it does not get used up in the reaction. It is basically there for most cases to facilitate the reaction occurring faster. It usually can find a nice alternative pathway for the reactants to get together in a more efficient way for that reaction to take place. A lot of times you will see catalysts written on top of the arrow. They could be something like a metal. They could be something like it's an acid or something like that, H plus. Um, for example, if you had gas molecules that are flying around and they want to come in contact with each other, you have to basically just wait for them to find each other, basically. Sometimes you could add like a catalyst, like a metal piece of catalyst, where they're kind of attracted to that. And what that does is just puts everybody in a closer proximity to each other. And that's going to initiate reactions to occur a lot faster than just hoping they're going to run into each other as they're flying around. Most catalysts are usually positive catalysts, which means you're usually used to speed up a chemical reaction. There are actually negative catalysts which actually slow down the reaction. But I would say in your conversations that you have with people about catalysts, I'm not sure why you're doing that anyways, but usually people are talking about catalysts in terms of speeding up the reaction. As we will talk a little bit about at the end of this chapter, catalysts can be homogeneous, like a homogeneous mixture, which means the catalyst and what's reacting are in the same phase. They're all liquids, or there may be gases, or solids, or something like that. Heterogeneous, they're in some different phases as well. The concentration is also a really important part. Usually, the larger concentration, the more things are available to react with one another. As you may know, molarity, right, is technically moles of solutes over liters of solution. It is the solute stuff that is the stuff reacting. So when you have a larger concentration, you have more solute. More solute means you have more things, for example, in a solution floating around ready to react in there. Gases also depend on pressure. Higher pressure, the higher concentration of a gas, because as you remember from Boyle's law, right, the higher the pressure, the smaller the volume, right? So the higher the pressure, now you have a smaller volume, and now all the gas molecules are really near each other. So that's going to increase the number of collisions and probably the reaction basically taking place. And obviously, the concentration there depends on molarity. Higher the molarity, usually you will have a much faster rate. Lower the concentration, you'll have probably a little slower, which is what we saw when we looked at those rates at the different times on that kind of earlier graph. It was much faster at the beginning and then kind of slowed down as you got to the end. That's because at the end we had a much lower concentration of reactant molecules, which again is going to take longer for everybody to kind of get together and find each other. And that is a great place to stop. Any questions on any of that there? All right.